we'll start with our problem. So our problem says, set up an integral for the function f of x, y, z for the region where x is greater than or equal to 0, y is greater than or equal to 0, z is greater than or equal to 0. We sometimes call that the first octant. Z is less than or equal to 1 minus x squared, and z is less than or equal to quantity y minus 1 squared. See the picture. So here's the picture. We follow the traditional labeling. So this is our x, our y, and our z. And so you have this beautiful shape. And you have 5 options, A, B, C, D, or E. Which one of these 5 is correctly describing the region? Do we have a guess? Preferably we have an answer. B or D? D. D is the correct answer. Now, what's going on? Well, you start by saying, look, all the integrals are in the same order. So that says the inner integral is an x. So I can think about what's happening just with the inner integral by saying I'm going to be moving back and forth in the x direction. So it's like, okay, if I'm moving back and forth, the back side, that's going to be the plane x equals 0, also known as the yz plane. The front side is this face, which depends on x. Well, I need to have my bounds in terms of x. So I rewrite z equals 1 minus x squared as x equals 1 minus the root z. So the integral, nothing else. I know the inner integral has to be 0 to the square root of 1 minus z. How much does that knock out? All the rest. So just by saying what's the inner layer, the answer has to be D. If you then take the x-axis, grab it, and then pivot to the point where you're looking down the x-axis, you'll see this piece of a parabola in the yz plane. You see that curve z equals 1 minus y squared. And that says that this part gives us our 2 outer layers. Since it's the order dy dz, well, y goes from 0 to 1. Z goes from 0 to y minus 1 squared. All right. So there you go. Now, you will want to get comfortable, at least tolerate, setting up and working with these multivariable triple integrals, because it's going to be on the exam. In some way, shape, or form, it's going to be on the exam. Be it multiple choice or long answer, it's coming. And once you know it's coming, it's like, well, let me be ready for it. All right. Any questions on the problem? Out of curiosity, which way would you not want to integrate this problem? Every way. Oh, that's sad. When we set up x as inside layer, it was pretty straightforward, relatively speaking. We went between 2 surfaces. If you integrate with respect to y, what will happen? You'll go between 2 surfaces. So your back surface is this y equals 0, and this front surface is 1 minus square root of z. Now, what happens if you integrate with respect to z?
Pain, never-ending pain.
Well, pain, never-ending pain. No, that's not quite true. What happens if you integrate with respect to z? If we look in the xy plane, you'll see it looks like a square here. And if you take this circle, so there's a quarter circle, in this part, that's where this sloped face is. So that's your surface z equals y minus 1 squared. That's what's the bound above. In this piece, that's where this part captures it. You get z equals 1 minus x squared. Which means if you were to have the inner layer be z, you couldn't do it as one integral. You'd have to break it up into 2 integrals. So there are less desirable ways. Maybe we should put it like that. There are less desirable ways. All right. So today, Thought for today. Shui Wu Zhijing. Now, I'm not very good with my Chinese pronunciation. My wife, she's from China, and she was laughing at me as I was trying to practice saying that. But the sentiment, there's always more to learn. Now, this might sound depressing, or it might sound encouraging. But the statement is true regardless. If you say, oh, there's always more to learn, and that excites you, it's like, that's wonderful. I'm enjoying it. That means whatever you're doing, you found your calling in life. Keep doing it. And if you say, I dread it, well, maybe you haven't quite found your calling yet. Or maybe it's time to learn to be passionate about things. Now, there's lots of ways that people say this in many different cultures. It's not just a Chinese saying. Among jugglers, there's a similar saying where you might say, well, look, I've learned to juggle 3 balls. And they're like, great. What about 4? Oh, okay, so I've learned to juggle 4 balls. Sudden gust of gravity there. And they say, great. What about 5? I'm like, okay, no, forget it. Hopeless. But so in juggling, the expression is, there's always one more ball. There's always something you can do. All right, further to go. Now, goal for today. We've learned about integration, and we want to talk about applications. And a lot of times when we start talking about integrals, everybody automatically goes to, integrals are about areas, or they're about volumes. And that's true that you can use integrals to find those things. So for instance, if we integrate over a 2-dimensional region, 1, what we're capturing is the area of that region. If we integrate over a 3-dimensional solid, 1, we're capturing the volume of that solid. But we could also just, in a similar way, integrate over a 2-dimensional region, integrate the height of the solid that's above that region. And again, that's capturing volume. So definitely there's geometric applications, and we will do more. A fun one to look forward to, which we'll probably spend a day on, is surface area. That's going to be a fun one. You might say, isn't that just area? Well, there's a little bit more to it. Good times. So, the thought for today is integrals are more than just geometry. Integration is what? It's about finding the total. We're looking for the total of something. Now, the thing is, well, what kind of things can we do? Well, if you can understand anything locally, then the idea is to say, well, let's take our big thing we're trying to understand, which is hard because it's not constant. We're really good with constant stuff. It's like we're really good with flat stuff. So we take our big thing and we break it up into little parts. And then on each little part, we say, well, look, because it's a little part, I can understand little parts. I can treat my things I'm interested in like a constant, and I can do my computations. So you break it up into pieces. You say, okay, what's happening on each little piece? And you add the pieces together. That's what integration is. So when we talk about integration, there's sort of 2 pieces to it. The first part, these symbols, they look like you've taken the letter S and you've stretched it really long and thin. That's S for sum. So, integration indicates adding. The number of integrals indicates the dimension of what you're looking at. So this, for example, would say, I'm looking over a 3-dimensional type object, and I'm adding things up. Now, what are you adding? You're adding the contribution from the pieces. Well, what does that mean? It depends on the problem. And so we're going to look at physics applications today, partially because physics wants us to help teach students to be ready for their physics classes, but also because it's a setting where a lot of people can build up intuition. All right, so our plan today, do some physics. In the interest of full disclosure, I never took a physics class in college. So my physics knowledge stopped at sophomore year in high school. So if you're looking for me to say anything profound, there will not be anything profound. It's worse for chemistry. I've never had a chemistry class. So, okay. And now you're thinking like, why did they let him teach? I have had math classes, just to be clear. All right. So we'll start with mass. So mass is like, okay, you have a region, and you want to know how much mass is there. So this is not too bad if we have a region which is very simple shaped and a density associated with which is constant. Now, when we talk about density, that's mass per unit. So it might be mass per area. If you're in 2 dimensions, it might be mass per volume. If you're in 3 dimensions. So if you have a simple shape, constant density, easy. What if you don't? What if you have a density which is varying? What if you have a shape which is weird? Then integration can help a lot. So the idea is we take our object, whatever it is, and we just take it and we cut it into little tiny pieces. Slice, 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 slice. Slice, 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 slice. And then we say, look, what's the mass of this little tiny piece right here? Well, it's the density of that little piece times the area of that little piece. So what we're really doing is this inner part, this is the mass of a small piece. And then what's going to happen is we're going to add them up. So we're adding up the little masses, and that gives us our total mass. So oftentimes you'll see the formula is, oh, it's this delta xy dA. I like to remember it as density dA, because that helps me understand where the pieces come from and how they fit together. For 3 dimensions, same thing. We're adding up density dV. Now you might say, wait, shouldn't they be different? Well, there is a subtle difference that's not being pointed to. Namely, when we talk about density here, this will be density per square unit. They may be like density per inches squared. Where for here, it would be density per inches cubed, mass per inches cubed. But other than that, the idea is basically the same. So no big surprises. By the way, I say mass, substitute it with whatever else you want to do. We're just trying to find totals. For instance, you can talk about electrical charge. Maybe you have an electrical charge in some sort of 2-dimensional or 3-dimensional region, and you want to say, well, what's the total charge? It's the same philosophy. Break it up, add it up. All right. So our first problem. Find the mass of the region in the plane, and sometimes you'll hear the word lamina. So if you ever see a problem that says lamina, it just means a flat 2-dimensional shape. That's what it is. So if you see lamina, 2-dimensional shape. And we're bounded by x equals 1 and x equals y squared. Okay, so let's quickly sketch that. What does x equal 1 look like? A line. Horizontal or vertical? Vertical. Good. X equals 1. Now, x equals y squared, what does that look like? Parabola. But has anything happened to it? Yeah. It's going to open sideways. To the right, to the right. Okay. So, that means our region is this region here. And our density isn't a uniform density. Our density is given by xy squared. So, since we very conveniently have the formula, we can say, well, the mass is the integral over our region of xy squared dA. But it didn't say set up the formula for mass. It says find it. So we have to find it. So that means we need to do iterated integrals. Pretty much the only way we can find integrals, unless they are super trivial, like integral of 1, where the region is a circle. It's like, we don't have to do that one. Here, it's not trivial. So we have to do iterated integrals. So we have to make a choice. Do we want to do dx dy or dy dx? So a quick reminder, dy dx would slice this way. These are the dy dx slices. Whereas dx dy would slice that way. Now, you will get the same answer, but the journey might be slightly different. So which one do you want?
dx dy.
Why are you recommending dx dy?
One integral.
Well, they would both be one integral because it's consistent in both cases. But I think dx dy, the nice thing about dx dy is I won't have to deal with square roots. So if I have dy dx, I'm going to have to deal with square root of y for the top and minus square root of y for the bottom. So let's do dx dy. Again, if you're like, I'm stubborn, Steve, I'm going to do dy dx, you'll get the same answer. No worries. Okay, so dx dy. Let's set up our bounds. Where do we hit? Where does y squared match with 1? 1 and negative 1. So where does y go from? Negative 1 to 1. Where does x go from? X goes from y squared to 1. All right? Any questions on that? Okay. Well, now we just carry out the integral. Integral negative 1 to 1. All right. When we integrate, what are we integrating with respect to in the first round? X. All right. Notation matters. So how do we treat the y squared? Constant. So what is the integral? 1/2 x squared y squared. Evaluate that from x equals y squared to x equals 1. dy. So this becomes integral negative 1 to 1. We plug in x equals 1, we get 1/2 y squared. Plug in x equals y squared. Y squared squared times y squared will give us y to the 6, right? The y squared squared is y to the 4th, and then there's one more y squared. All right, dy. Okay, now we can take advantage of symmetry if you want. Do you want to take advantage of symmetry or? Yes. Notice our bounds are symmetrical about 0. What can you say about this function? Is it an even or is it an odd function? Or is it a mix? Even. It's an even function. Now here's the great thing. If you have an even function and you're symmetrical around 0, it's the same as just doing twice from 0 to 1. So this is using symmetry of even functions. So I'm not actually integrating here. I'm just using symmetry. So if you're in case you're like, whoa, wait, what happened? So an even function has this nice symmetry about the axis. And I'm just saying, well, if I'm going from negative a to positive a, all I have to do is go from 0 to a and double, because it'll match the other side.
Is it even because the powers are even?
Yes. Even powers, even function. But there are other things. There's cosines even, sines odd. But if you have a polynomial, even powers, even function. Odd powers, odd function. It's almost like they meant for that to happen, because they did. Okay, so we've carried this integral out. Now notice the 2 1/2 cancel, so that'll make it a little bit easier. So we have 1/3 y cubed minus 1/7 y to the 7th. And we're evaluating from y equals 0 to y equals 1. And the reason I like to use symmetry is I like 0. 0 is a friend. When you plug in 0, what do you get? 0. And when you plug in 1, 1 cubed, 1 to the 7th, what are those?
1/3 of the 7th.
Well, they're 1, right? So 1/3 minus 1/7, common denominator would be 21. So 7 over 21 minus 3 over 21 gives us 4 over 21. Now, we don't know any units because they didn't supply any units. If you care about units, take more physics classes. because they seem to care about units. All right, so that's mass. Break things up, integrate density dA, integrate density dV. All right, any questions about mass? Okay, in that case, let's take a moment here. So, the next topic is moments. And when we say moment, we usually refer to what's called the first moment. On a side note, you could think of mass as the 0th moment. We'll see why in a second. But okay, what does moment do? Well, you want to know sort of two things. You say, look, I have my mass, but I want to talk about how it relates to some object. So I also want to have a distance involved. And the keen-eyed observer might say, I notice you didn't say distance, you said distance, distance. Why did you put quote marks there? Well, we put quote marks there because technically it was not distance, it can have negative values. It's really a position relative to some object. So it is possible it could be negative. That's a small technicality, don't worry about that. It's one of the reasons why we say you don't need to throw in absolute values. That's what that means. All right, so how do we compute it? Well, we already know how to do mass. That's your density dA. So this last part says, okay, here's the mass of the piece, and then here's the distance of the piece. So that says this whole thing, this is the moment of a small piece. And then add the pieces together. So, great. Distance times density. Now, in 2 dimensions, there are 2 things we talk about moments with respect to. And those are the axes. So we have the mx, my. So let's quickly remind ourselves, if we are at a point x, y, and I want to say, how far am I from the x-axis? The strong temptation is to say, I'm x away. But that's not right. How far are you from the x-axis? Well, because we need to answer this question, right? Oh, wait, no. Oh, you meant the variable y. Oh, my God. I can't believe I made that mistake again. Oh, how many times am I going to do that? Okay, so yes. So the distance, so you can think of it as y is actually measuring not how far along the x-axis you move, but how far away from the x-axis you move. In a similar way, when I want to find my distance to the y-axis, it's that x. So that's why you'll notice here, when we talk about moment with respect to x-axis, it's not x, it's a y. So you have to be careful with your notation. It's really tempting to say, oh, m sub x, I should throw an x in there. No. Be careful. But the punchline here is the distance is to the x-axis is y. Here, when we talk about the moment with respect to the y-axis, the notation m sub y, that distance is x. So again, distance, density, dA. In 3 dimensions, what goes on? Well, in 3 dimensions, when we talk about moments, the 3 kind of moments we care about, at least for our class, they don't have to be planes, but they will be planes. Those are the ones we care about. So it's moments with respect to planes. So again, you can think of, suppose I'm in 3-dimensional space, and there's a point, x, y, z. Now, if I want to find the distance between a point x, y, z to the x, y plane, what gives that? So I drop straight down. What's this measurement? It's z. So that's, again, the distance to the x, y plane. Distance, density. I should have labeled my axes. X, Y, Z. If I'm in the XZ plane, how far away am I? Y. I won't do it twice within a few minutes. That's just too extreme. I got to space it out. I know you were nervous there. It's like, oh, well, how often is he going to do this to us? And then finally, to the YZ plane, that's x. So these are coming from distances. So once you understand that they represent distances, then it's like, oh, I don't have to memorize 3 formulas. I memorize one principle. And once I understand the principle, then I can adapt it. So we could change it to say, well, maybe I want the moment not with respect to the xy plane, but moment with respect to the plane z equals -2. What would change if instead of the xy plane I said the plane z equals -2? The distance part would change. So how far am I away from the plane z equals -2? Z plus 2. That's how far away you are. So then it's like, oh, great. So now you don't have to memorize millions of possibilities. Again, it's memorize principles. And once you memorize principles, then you're good to go. Now, how do we often use moments? Well, our main way we use moments is doing center of mass. So we're going to talk about center of mass for a few minutes. And there's a couple of ways to think about center of mass. It's a balancing point, and oftentimes you'll say, well, you can imagine if it's the single point on which you balance. So for example, you can try this if, I don't know if we have any cafeterias that still use trays, but if you go to a place which has trays, and you just put your hands up, and you're holding up a tray, and then just slowly bring your fingers together, where will you end up? You'll end up at the center of mass. It will balance out. And so what is that point? Well, again, it's where everything balances. But how do we find it? Well, what we're really after when we talk about center of mass is we're averaging the locations of the shape. However, it's a weighted average because the shape may not be uniform in density. So some parts are heavier. They need more. They need to count for more. So here's a very, very simple example. Suppose I have 3 weights. One weight has value 3 at location 0. Another has value 2 at location 4. The last one has value 9 at location 10. Where is the center of mass? How do we find it? Well, the center of mass, which is usually if you see a bar on top, that means an average. So it is an average. So think of this bar. Bar indicates average. So the average, well, an average is, we're going to have a ratio. First off, we say, let's look at the individual contribution. So location 0, that got 3 votes. Location 4, so I'm thinking of the weight here, you can think of it in terms of votes, had 2 votes. And location 10 had 9 votes. So I'm taking location times weight. Then I say, okay, well, how many votes were there? 3 plus 2 plus 9. And we add these up. What do we have upstairs? 98. What do we have downstairs? 14. 98 over 14, also known as 7. So that says the point of balance is at 7. Not at 5, halfway between the 2 extremes, but more towards the larger weight, because the larger weight gets more votes. It gets to dictate what's going on. Now for us, we want to do the same thing. So we say, well, what's going on upstairs is we're adding up locations and masses. Locations times masses. Well, locations, that's like a distance. So suppose I wanted to do an x bar for a 2-dimensional region. So I want to add up a bunch of things. What do I want to add up? The x location times our density dA, which is our mass. Downstairs, I'd want to add up just the total number of what I previously called volts, density dA. Well, what's another name for the downstairs? Mass. What's another name for the upstairs? I'll give you a moment to think about it. It is a moment. Okay, good. But which one? It's moment with respect to the y-axis. Because remember, this is, if we think of this as distance density instead of location density, distance to what? X is your distance to the y-axis. So, for 2D, our center of mass can be computed using the following. X bar, y bar is moment with respect to y divided by mass, moment with respect to x divided by mass. In 3D, same kind of argument. What's the center of mass? Well, again, the average y, average x, average y, average z is, there's three terms. They all look like ratios. What goes in your denominators? M, the mass. That's just as under here, that's the total mass. What goes in the numerators? Let's start with the first term. Moment with respect to what? YZ. Because that's the moment where the distance is x. Similar to what we have here. What goes in the second category, the second entry? XZ, yep. And the third? XY. All right. Now, one last note here. Pro tip. Center of mass obeys symmetry. So, if you have symmetry, then you can narrow down where your center of mass is. Now, when we talk about symmetry, you have to be really careful. So, symmetry means in terms of the shape, but is that sufficient? No, because you also have to look at the density. So, let's suppose we had something like the following. Here we have a circle. Let's say this is x squared plus y squared equals x. So this is the point 1. And we'll fill it in a circle here. And now I tell you that the density is x. What is that telling us about this shape? Can we say anything about the center of mass at this point? It's what? It's closer to 1, right? Because in some sense it's denser here, but then it starts getting sparse on the other side. So there's more density to the right than to the left. Now the circle is super symmetrical. However, the density here is not. So when we're looking for symmetry, we're basically saying we want to imagine you have a spatula, you pick your shape up, turn it over, and put it back down again. And what you want it to be is exactly the same. The shape lines up, the density lines up. And if you can find anywhere where you can do that, that's a symmetry. Does this have a symmetry? Yeah, where? Yeah, the x-axis. So here, the x-axis is a line of symmetry. Now, that says that the center of mass has to be on that line. So what conclusion do we make? We can say that y bar equals 0. So in many problems that we ask on exams, historically, when we find the center of mass, one coordinate is a freebie. And then the other coordinate we have to work. All right, how are we doing with time? Oh my goodness. There's a lot to talk about today. Should we do a center of mass one really quickly? Yes. I know you're anxious. You're gnawing at the bits like, Steve, I want to do a problem. Well, I hope we get time for that. Okay. Find the center of mass of the region in the plane, the lamina, bounded by x equals 1 and x equals y squared, with delta xy equals y squared. Now, this problem might sound vaguely familiar. Have we seen anything like this before? No? Oh, that's a shame. It would have helped if we'd seen something like it before. You sure? Got to start from scratch. Okay, so our density xy squared. All right, now, in the interest of full disclosure, we have seen this before. Do you remember what the mass is? 4/21. Okay, so that we can recover from last time. So we don't have to do 2 computations, we just have to do 1. Does this have any symmetry? Yes. What symmetry is there? The x-axis. Now that's just from the symmetry of shape. That's our only hope. And then you have to say, well, if I turn it and flip it over, do I preserve the density? And thankfully the y squared helps with that. So yes. So this is a line of symmetry. And so, what does that tell us? Y bar equals 0. So what is it that we need to compute to finish finding the center of mass? X bar. And what do we need to do to compute x bar? So x bar is my over m. We've got the m, so we need the moment. All right, so we're going to go through and remember, what did we find? Moment with respect to y. Integral, I'm going to use the same bounds that we did before. Y squared 1. Then we have distance, we have density, and dA. What goes into our distance slot? X. Good. Make sure you're putting the right value in. Just because that says y, you don't want y. So you say, well, I'm just left with x. All right. And then otherwise, it's the same kind of computations we did. So, oops, not dA. I'm sorry about that. dx, dy. So we integrate first with respect to x. We'll have 1/3 x cubed y squared, evaluated from x equals y squared to x equals 1, which becomes the integral -1 to 1 of 1/3 y squared. Oh, that's not bad. Minus 1/3 y to the 8th. Again, we'll use our symmetry, pull out our factor of 3, or 1/3, 2/3 integral 0 to 1, y squared minus y to the 8th. So that's 2/3 times 1/3 y cubed minus 1/9 y to the 9th. Evaluate from 0 to 1, which is 2/3 times 1/3 minus 1/9. All right. 1/3 minus 1/9, also known as 2/9. So 2/3 times 2/9, which gets us 4/27. Okay, so is this our x bar? No! Why not? That's our my. Okay, so our real x bar, now we have to do our computation. This is really our 4/27 divided by our mass, 4/21. Well, the 4's, this is going to be written as 4/27 times 21/4, so that the 4's cancel. Do 21 and 27 have any common factors? Yeah. Yeah, so you can divide by 3, and we can end up with 7/9. All right, so our center of mass, x bar, y bar, is 7/9, 0. Now, before we run away from this problem, not that we're scared, but we have other things to run towards, is it reasonable? It would say that the center of mass is, roughly speaking, right around here. But you'll notice that we are definitely more mass to the left, and also especially in the upper corner. So there's a lot of mass in this piece. Now, what would be unreasonable? If we had gone that the center of mass was here, is that reasonable? So where I have this dot. Is that a reasonable answer? No. The center of mass kind of has to be center-ish. So if your center of mass is not somehow center-ish in your shape, check your work. Did you remember to divide by m? That's a common mistake. And then you won't make that mistake again. All right, well, so we've had mass. I told you mass is like the 0th moment. We also had moment, which is like the first moment. So where do you think we're going next? We're going to the second moment. All right. So what is the second moment? Well, that's called inertia. And what the idea of inertia is, you're meant to measure a tendency to stay in current shape, current state, excuse me, not shape. So what's the quantity? How do you compute it? The key is it's the second moment, so it's distance squared. Now you might say, does that mean that there's a third moment, and a fourth, and a fifth? Are there infinitely many moments? Yes. Are we going to talk about them? No. But other classes, you might. There's actually a beautiful thing called the moment generating function, but that's a topic for a completely different class. So we stop here. So, all right, so the key to remember is inertia is distance squared density dA. Again, this density dA is just saying the mass. So it's mass times distance squared. And so that's the inertia of one little piece, and then you add the pieces up. And we only talk about inertia in the plane, at least as far as I know. We've never historically have given an inertia problem in 3D. Okay, so there are now 3 things that we talk about with respect to inertia. There's the x-axis, and we've already talked about how if I'm at a point, x, y, the distance to the x-axis is y, so that's why you see a y squared for inertia. So I for inertia, x, x-axis. The y-axis, and the distance there is x, but then there's one more, which is the origin. I0. I like to also call this IZ, but if you look in some of my old notes, you'll see I call this IZ. I think I might even call IZ on the handout. Do I? Yes. So, what's this distance? Well, square root of x squared plus y squared. Like, that looks terrible. There's a square root. But notice, you want a square of that. So you get rid of the square root. So it becomes just x squared plus y squared times density dA. All right, so there's inertia. All right, now we have a few minutes. So let's have you do a problem. Your turn. And this is from an old, I think it's an old final problem. But it wasn't a multiple choice, but we'll give it to you as a multiple choice. Find the inertia with respect to the origin for the region consisting of the Archimedean spiral 0 less than or equal to r less than or equal to theta less than or equal to pi with density delta equals 1. Do you want to talk at all about this region before you start, or are you ready to go? You're like, I see this region. Boom, yes. talk a little bit? Okay, let's talk about R. What's true about R? 0 less than equal to R less than equal to theta. So that's the Archimedean spiral. It starts at the origin, and as you go out, it goes further and further out. So now, what about theta? Well, what's the largest value theta can get? Pi. So that's over here. What's the smallest it could get? Well, R, but how small can R get? 0. So the Archimedean, this is telling you this region here. So this is the shape of your region. All right. Spoiler alert, you might want to try polar. Wink, wink.